Good morning everybody. Last time we had started with the surface chemistry and the main topic of the surface chemistry, that is the adsorption. So we had seen why the adsorption takes place. The adsorption takes place due to the unbalanced field of force at the surfaces of either liquids or the solid. Therefore, we had seen the definition of the adsorption. Adsorption is nothing but the collection of a substance, one substance on the surface of the other. Simply that is called as the adsorption. The difference between the adsorption and absorption we have seen. The adsorption is a surface phenomenon while absorption is a bulk phenomenon. In the adsorption, the molecules are present only on the surface of the other substance, while in the absorption, the substance get evenly distributed in the bulk. That is nothing but the absorption. Then we had seen the types of adsorption. The two types are there, the physical adsorption and the chemical adsorption, or which is also called as chemisorption. This classification is done on the basis of the types of the forces which are formed between the adsorbent and the adsorbate. The adsorbent is nothing but on the surface of whose adsorption takes place, that is called as the adsorbent, and the substance which adsorbs or collect on the surface of the other, that is called as the adsorbent. And the types of the forces in between these two is the basis of classification. When these forces are weak of the type van der Waals, therefore that type of adsorption is called as the physical adsorption, while the chemical adsorption is when the bonds or the forces like chemical forces or the chemical bonds are formed between in these two. The type of adsorption is called as the chemical adsorption. We have seen the point of difference in between these two. We have seen that the physical adsorption is a multi-layer, while the chemical adsorption is a single layer. The amount of energy which is evolved is very much greater in chemical adsorption as compared to the physical adsorption. The physical adsorption is non-specific, while the chemical adsorption is very specific type of adsorption. These are some point of differences that we have seen. Now let's go further. The adsorption isotherms. What the adsorption isotherm is? Actually, this is the relation. Adsorption isotherm. This is the relation between. Actually, this relation is considered to be at constant temperature. So, a relation at constant temperature between the amount of the substance adsorbed and the pressure or concentration at equilibrium is called as the adsorption isotherm. I will repeat the definition. Adsorption isotherm, this is a relation at constant temperature between the amount of the substance adsorbed and the pressure and the concentration at equilibrium. This relation is called as the adsorption isotherm. Two adsorption isotherms we have. Friedrich adsorption isotherm and Langmuir adsorption isotherm. These two adsorption isotherms we have. Out of that, we will see first what is a Friedrich adsorption isotherm. This obviously the relation is same, that is between the amount of the substance adsorbed and the pressure or the concentration. Friedrich adsorption isotherm, this shows the variation of the extent of adsorption and the pressure or the concentration at equilibrium, and the relation here is x by m is equal to k into p raised to 1 upon m. This is what is the equation of Friedrich adsorption isotherm. Now, what is x? X is Now here, as the pressure is being here, that means here which type of adsorption is considered? The adsorption of the gas on the solid surface. This type of adsorption system is considered here, and that's why the pressure term is here. If the adsorption of the solid particle from the solution, they are adsorbed on the solid surface, in that case instead of pressure, concentration term comes. Let's first see in relation with the pressure. Now the X is the amount of the gas adsorbed. Amount of the gas adsorbed. M is this amount, or we can say mass of the gas adsorbed, because M is the mass of the adsorbent. That means the solid surface on whose surface the adsorption takes place. The mass of that adsorbent is M. Therefore, X by M is mass of gas adsorbed per unit mass of adsorbent. So X by M ratio, this is nothing but mass of gas adsorbed per unit mass of the adsorbent, or this is also called as extent of adsorption. X by M is also called as extent of adsorption, and the Freundlich adsorption isotherm shows relation between the extent of adsorption and the pressure, and this is the empirical relation between these two terms, where this K is a constant, K and N are the constant, and these depends on the nature of the adsorbent as well as the nature of the adsorbate. On this means these two K and N, these are the constant which depend on the nature of the adsorbent and adsorbate. Now this relation of Freundlich adsorption isotherm, this relation is valid, or this holds over a limited range of a pressure. This relation holds at the limited range of a pressure. Hence, therefore, the Freundlich adsorption isotherm is defined as the variation of the extent of adsorption with pressure at equilibrium at constant temperature over a limited range of a pressure is called as the Freundlich adsorption isotherm. So therefore, this means that this relation is valid only for a limited range of a pressure. Here, this N is an integer. This is an N which is a constant. It has the value always greater than 1. The N, a constant, which have always the value greater than 1. What this means? This means that obviously this is here in the denominator, and if it is greater than 1 upon which is greater than 1, so this value will be very small. So therefore, the increase in the pressure will not increase this term proportionately, right? And therefore, this shows that on increase in the pressure, the extent of adsorption does not increases proportionately. But this is true only for the moderate range of pressures. If we plot a graph of extent of adsorption versus the pressure, if this graph we plot, therefore it is found that such type of a curve is formed. Now this curve is divided into the 3 parts like this. Here this is at low pressure, this part at intermediate pressure, and this part is at high pressure. Now what this parabolic curve tells us? From From this parabolic curve we can say that at the low pressures there is a linear increase in the amount of adsorption with the pressure. Linear increase is there, right? That means here x by m is directly proportional to P. This relation is at lower pressure because at low pressure the extent of adsorption increases linearly with the pressure, and hence here x by m is directly proportional to P, while at intermediate pressure the curve has bent. What this shows? This shows that at the intermediate pressure range the extent of adsorption does not increases proportionately with the pressure. म्हणजे जसं प्रेशर मध्ये ज्या प्रमाणात इन्क्रीज होतो त्या प्रमाणात मात्र एक्सटेंट ऑफ एब्झॉर्प्शन मध्ये इन्क्रीज होत नाही, जसं आपल्याला लो प्रेशर रेंज मध्ये पाहायला मिळतो. आणि त्याच्यामुळे या पोर्शन वरती x by m is proportional to p raised to 1 upon n, where n is always greater than 1. So this relation is only for a limited pressure range. At intermediate pressure this relation is good, and at the high pressure we can see that x by m is constant. A limiting value reaches, graph कॉन्स्टंट हॉरिझॉन्टल झाला. याचा अर्थ तुमचा प्रेशर जरी वाढत असेल तरी सुद्धा एक्सटेंट ऑफ एब्झॉर्प्शन ची व्हॅल्यू मात्र इन्क्रीज होत नाहीये. याचा अर्थ ॲट हायर प्रेशर द एक्सटेंट ऑफ एब्झॉर्प्शन reaches to a limiting value. Therefore, from this graph what we can say about the Freundlich adsorption isotherm? We can say that the Freundlich adsorption isotherm is applicable only for the limited range of pressure, that is it is applicable for the intermediate pressure and not all the pressure ranges. It is not applicable at lower pressure as well as the higher pressure. So this Freundlich adsorption isotherm is not having a theoretical importance. Why? Because it is applicable over a limited range of a pressure. This relation, if we write the relation for solid and the solution system, that means the solution which adsorbs on the solid surface. For such type of a system, x by m is equal to k into c raised to 1 upon n. Instead of pressure, just we substitute the concentration term. When the solute particles from the solution they adsorb on the solid surface, in that case the concentration of the solution has to be considered, and therefore the relation for that system becomes x by m is equal to k into c raised to 1 upon n. This is what is the relation for solid solution system. Here also the relation is true only for the limited range of concentration. If you take log on for this both sides, for this equation if you take a log, so log of x by m is equal to log of k plus 1 upon n into log c. This is what is the equation will become, right? These two terms are in product, so therefore if we take their logarithm there will be addition of their logs. For this term, this is the power of the term, so according to the rule of logarithm it will be in the product, right? So log of x by m is equal to log of k plus 1 upon n into log c. Now if I plot log c on the x-axis and log of x by m on the y-axis, therefore see now this we have plotted on the y, this we have plotted on the x. Therefore this equation takes a form of a straight line of the equation y is equal to mx plus c. Therefore this line will be as like this, and this will be obviously an intercept, that is log k, and the slope will be 1 upon n. So this is how the graphical representation for the Freundlich adsorption isotherm is. This graphical representation. We are going to compare with the other type of adsorption isotherm. Alright, so this was about the Freundlich adsorption isotherm, and we have seen that this Freundlich adsorption isotherm has no theoretical significance or the importance, because it is applicable over the limited range of a pressure. It is not applicable at the higher pressure. Alright, now let's see the second type of adsorption isotherm, and that is Langmuir adsorption isotherm. Langmuir adsorption isotherm. Now, what the Langmuir adsorption isotherm is. Now, the Langmuir adsorption isotherm, again, it shows the same relation, that is the variation of the extent of adsorption with the pressure at equilibrium and at constant temperature. But Langmuir, it actually forms the basis of adsorption isotherm. He actually forms the basis of the adsorption isotherm with the help of some important assumptions, and his theory of adsorption was accepted and it has a theoretical significance also. So Langmuir derived the relation between the extent of adsorption and the pressure depending on some assumptions. Let's see what those assumptions are. The first assumption is that the adsorption which is taking place between a gaseous molecule and the solid surface. In this system, a single layer is formed of the adsorbed molecule. This is the first important assumption of the Langmuir adsorption isotherm, that a unimolecular layer of the adsorbed molecule is formed on the surface of the solid. Actually, the solid surface consists of elementary spaces, and each elementary space can adsorb a single gas molecule, and therefore the adsorption layer is a single molecule thick. That means only a single layer is formed, and the intramolecular forces, they fall off when the thickness of the adsorption layer increases than the single layer. What it means? When a single layer is formed, on that, when the second, third, fourth layer will be formed, the intramolecular forces between the molecule, they fall off. Therefore, the molecules they do not bind themselves with each other, and that is why a single molecular layer is formed. The next layers, they do not get adsorbed because the intramolecular forces, they fall off or they vanish off. Hence, the first very important assumption is that the unimolecular adsorption layer is formed. This is the one or the first assumption. Unimolecular layer of the adsorbed molecule is formed. Now, the second, the solid surface has uniform properties of adsorption. The solid surface which is considered it has uniform properties of adsorption. What it means? This means that all the elementary spaces which are present on the solid surface have same affinity for the gas molecule. That means every space has the same affinity. Therefore, every space can adsorb a single molecule only. This is what is the uniform adsorption properties all the elementary spaces are having same affinity for the gaseous molecule, and hence therefore all the spaces can adsorb a single molecule. So solid surface has uniform adsorption properties. The next assumption is that the adsorption of a molecule on one elementary space has no effect on the adsorption properties of the label. एक मॉलिक्यूल एका एलिमेंटरी स्पेसवर ऍब्झॉर्ब झाल्यानंतर शेजारच्या एलिमेंटरी स्पेसचा गॅस मॉलिक्यूल्स साठी असणाऱ्या अफिनिटीवर फरक पडत नाही. दिस इज व्हॉट इज द अझम्पशन. Actually, this states that every elementary space has the same gas molecule affinity, and therefore every elementary space have one molecule. Once it gets adsorbed, a single molecular layer will be formed, and no change in the affinity will be there when one of the elementary space get adsorbed, which is the neighbor to one. So therefore, the third assumption is that no effect of adsorption of one elementary space on its neighbor, म्हणजे त्याच्या शेजारचा जो काही स्पेस असेल त्याच्या गॅससाठी असणाऱ्या अफिनिटीवर काहीही फरक पडणार नाही, असं हे तिसरं अझम्पशन आहे. आणि नेक्स्ट अझम्पशन, फोर्थ अझम्पशन, the gaseous molecule which are adsorbed on the surface, those gas molecules have some thermal energy, and due to that thermal energy, these gas molecules which are adsorbed, they may get detached from the surface and pass back into the gas phase. See, here two phases are there. Gas phase in the sense the gaseous molecule which are free, and the second phase is condensed phase. Condensed phase म्हणजे काय, जे गॅस मॉलिक्यूल सरफेस वरती येऊन ऍब्झॉर्ब झालेले आहेत त्यांची फेज म्हणजे कंडेन्स्ड फेज. काही मॉलिक्यूल्सला थर्मल एनर्जी असते, and this thermal energy, due to this thermal energy, the gas molecule get detached, म्हणजे सरफेस पासून डिटॅच होतात आणि पुन्हा गॅस फेज मध्ये जातात. याला डिसॉर्प्शन किंवा इव्हॅपोरेशन असं म्हणतात. राइट. सो therefore the adsorption process consists of two opposing actions. One is that is called as the condensation. And what is condensation? Condensation is adsorption of the gas molecule from gas phase onto the surface of the solid. This is called as the condensation. And the second action is desorption, or we may say it evaporation. The evaporation is nothing but the molecule from the condensed phase, they dissolve from the surface and pass back into the gas phase. That is called as the evaporation. So adsorption process consists of these two opposing actions, and at the equilibrium, the rate of condensation and the rate of evaporation are exactly same. The rate of condensation is equal to the rate of evaporation at equilibrium. This is a very important assumption of the Langmuir adsorption isotherm. And the last assumption is that the molecules which are adsorbed on the surface of solid, they get dissociated. Adsorbed molecule are dissociated. So these are what are the 5 assumptions of the Langmuir adsorption isotherm. Alright. Now, if I consider, now we are going to derive the equation of the Langmuir adsorption isotherm. For that, what we consider? We consider a surface, solid surface, which is 1 square centimeter. And in this, on this surface of the solid, this is the fraction which is adsorbed with the gas molecule. And this fraction is a theta. Alright, what we consider? We consider a solid surface which is 1 centimeter square. Let me start from here, so we will get the space for derivation. So this is the surface we have considered, which is 1 square centimeter, and this is the surface which is a theta, which is occupied with the gas molecule. Alright, therefore, how much is this is the occupied space or occupied fraction we have considered is theta. Therefore, how much will be unoccupied? Unoccupied fraction is equal to, this is total is 1, out of that theta is occupied, therefore 1 minus theta will be unoccupied. Alright, now according to the kinetic theory of the gases, the molecules which strikes the solid surface, their rate of striking the solid surface is directly proportional to the pressure of the gas. This is the assumption of the kinetic theory of the gases, the ideal theory for the gases. The striking rate of the gas molecule on the surface of the solid is directly proportional to pressure, and the other important thing that we have considered here is, as the layer formed on the solid surface is a single layer, that means that the gas molecule which strikes the surface get adsorbed. The molecules which just in contact with the solid molecule, they does not get adsorbed. The molecules which only strikes the surface of the solid, that only get adsorbed. And the second, according to the kinetic theory of the gases, the rate of a striking of the gas molecule on the surface is directly proportional to pressure. We are going to consider these two things during the derivation. Now, rate of condensation we are going to write. Now, the rate of condensation, that means the rate of adsorption, the gas molecule adsorbing on the surface. Obviously, this rate of condensation is directly proportional to the first thing, that is the pressure. And the second thing, the surface area available for adsorption. Now, the theta surface area is already covered. The surface area unoccupied, on that the rate of condensation will depend. That means the rate of condensation is directly proportional to the pressure, and the surface area which is available for condensation. So, rate of condensation, let me write in the short form, rate of condensation is equal to, I took a proportionality constant K1. So this is the rate of condensation is equal to K1 into P into 1 minus theta. Now, rate of evaporation. Now, rate of evaporation, that means the desorption of the molecules. The desorption of the molecule takes from the surface which is covered, right? The surface which is bare in the sense which is not occupied. From that, desorption will not at all take place because no molecules are present on that space. So rate of evaporation or desorption is proportional to the surface area covered, and the surface area covered is theta. Therefore, rate of evaporation is equal to a proportionality constant I have taken K2 into theta. Now at equilibrium, in the assumptions we have seen that assumption मध्ये आपली एक गोष्ट सांगायची राहिली पहा, ज्या ठिकाणी आपण अपोजिंग ऍक्शन्स लिहिल्या की ऍब्झॉर्प्शन ही जी प्रोसेस आहे हे लगेचच तुमच्या वहीमध्ये कुठेतरी क्लिअर करा की हे जे ऍब्झॉर्प्शन प्रोसेस आहे ही दोन अपोजिंग ऍक्शनची असते, एक म्हणजे कंडेन्सेशन आणि दुसरं म्हणजे इव्हॅपोरेशन. आणि त्यात एक महत्त्वाची गोष्ट नमूद करा, ऍट इक्विलिब्रियम रेट ऑफ कंडेन्सेशन इज इक्वल टू द रेट ऑफ इव्हॅपोरेशन. हे अझम्पशन्स मध्ये इन्क्लूड करा. ऍट द इक्विलिब्रियम द रेट ऑफ कंडेन्सेशन इज इक्वल टू द रेट ऑफ इव्हॅपोरेशन. That means these two equations we can equate. K1 into P into 1 minus theta is equal to K2 into theta. So therefore, I am multiplying with these terms inside. So K1P into 1 and K1P into theta, which is equal to K2 into theta. Now K1P is equal to, this term I am taking on this side. So I can take theta common, so theta into K2 plus K1 into P. Now therefore theta is equal to K2 plus K1 into P divided by K1 into P. This is what is the relation. Now this term we are taking on this side. So K1P divided by K2 plus K1 into P. This is what is the relation for theta. Now what we are going to do is, this is what is the theta value we have got. Alright, now the extent of adsorption, that is x by m, is directly proportional to the surface area covered. The extent of adsorption or the amount of adsorption is directly proportional to the surface area covered. That means that x by m is directly proportional to theta. Therefore x by m is equal to k into theta, where k is a proportionality constant. Now we are going to substitute theta from this equation. So therefore x by m is equal to k into k1p divided by k2 plus k1p. Let's multiply with this k inside. So k into k1p divided by k2 plus k1 into p. Now what I am going to do is, I am going to divide by k2 to the numerator and denominator. That means k into k1 divided by k2 into p divided by k2 by k2 plus k1 by k2 into p. Now therefore let this k into k1 into k2 is equal to a constant a, and k1 divided by k2 is equal to another constant b. Therefore what our equation becomes, x by m is equal to a into p divided by 1 plus, this get cancelled, therefore 1, and k1 by k2 is nothing but b. So this is what is the equation which is called as the equation for Langmuir adsorption isotherm, and this equation is applicable over all the ranges of pressure, and hence therefore the Langmuir adsorption isotherm has the theoretical importance. Now to towards graphical representation, what is done? This equation is divided by P. This divided by P. So what will become? The relation is x by m into P is equal to AP divided by simply P into BP plus 1. This P will get cancelled. Now taking the reciprocal of this equation, reciprocal, that means P divided by x by m, which is equal to BP plus 1 divided by A. This is what is the relation, and if this denominator is separated, that means for every term B divided by A into P plus 1 upon A. This is what is the relation which we have rearranged for graphical representation. Now, if I plot P by x by m on the y-axis and P on x-axis, therefore, obviously this is on y-axis, this is on x-axis. So this equation takes the form of a straight line. Y is equal to mx plus c. So this is how this straight line will be, and this is nothing but the intercept is nothing but 1 upon a, and the slope is b divided by a. And the straight line that we get from the Langmuir adsorption isotherm, it gives the good results. That means if we fed a same data to the Freundlich adsorption isotherm equation and the Langmuir adsorption isotherm, and if we do the graphical representation, therefore we get a very good straight line for Langmuir adsorption isotherm than the Freundlich adsorption isotherm. That means that the Langmuir adsorption isotherm is superior than the Freundlich adsorption isotherm. On the other test also, if we do the other test, therefore it is observed that the data which we fill in the two equations, that of the Freundlich and that of the Langmuir adsorption isotherm equation give the good results or the matching results. So this is how the Langmuir adsorption isotherm is superior over the Freundlich adsorption isotherm.